This lecture is going to cover one-factor analysis of variance, or one-factor ANOVA for short, as well as multiple comparisons, which is an extension of the one-factor ANOVA test. So let's suppose we want to compare the average math SAT scores for 5 students in 3 different majors. We have 5 computer science majors, 5 economics majors, and 5 history majors. We want to know if the average math SAT scores are equal across all 3 of these majors. So taking a look at the side-by-side box plots over on the right, we can see that the means do appear to be quite different. The computer science mean is somewhere a little bit above 700, the economics mean is around 650, and the history mean is somewhere around 550. However, there's also a great deal of variability within each individual group. Moreover, the sample size is pretty small. And so in the end, what we need is an inferential technique that allows us to compare 3 different means simultaneously. Up until this point, all of the inferential techniques that we've done that involve analyzing a population mean only dealt with 1 or 2 samples. We need some technique that can handle 3 or more groups. That's where one-factor analysis of variance, or one-factor ANOVA, comes into play. ANOVA is a statistical technique that's used to compare the means of 3 or more populations. ANOVA actually uses 2 different sources of variability in order to compare the means. First, we have between group variation. Between group variation measures the amount of variability that exists between the sample means of the individual groups. So between group variation basically looks to answer the question, how different are the sample means from one another? So in this case, how different is the computer science mean from the econ mean, and how different are those means compared to the history mean? The other source of variability that we have is within group variability. Within group variability measures the amount of variability that exists within each of the individual samples. So within group variation looks to answer the question, how different are the individual observations from one another within each group? So, for example, how different are the 5 computer science math SAT scores? How different are the 5 economics math SAT scores? And how different are the 5 history math SAT scores? Consider these 2 sets of box plots. The box plots up on top exhibit small between group variation. The reason that we have small between group variation is because these 3 means are very close together. Their values are about 40, 42, and 44, so we don't see a very large difference between these 3 means. On the other hand, these box plots also exhibit large within group variation. The reason that we have large within group variation is because the observations within each group are very far apart from one another. We have a lot of spread and we have a lot of overlap amongst these box plots. Each one of these ranges is about 40. Now in the box plots on the bottom, these are exhibiting large between group variation because these means are very far apart. They have means of about 3, 13, and 23. And unlike the box plots up on top, these exhibit small within group variation. These observations within the groups are very close together. There's absolutely no overlap across the 3 box plots. And the range for each sample is about 5. So we have large between group variation because the means are very far apart from one another, but we have small within group variation because the observations within each sample are very close. Now the ANOVA test takes a little bit of time to develop and to derive, so let's take things step by step. In ANOVA, let's say that we have k different groups that we are comparing, k different populations. The null hypothesis in ANOVA is that all of your means are simultaneously equal to one another. mu1 equals mu2 equals mu3 all the way out through mu k. The alternative hypothesis here is that at least 2 of these means are not equal to one another. In order to run our one-factor ANOVA test, we need the independence condition, both the groups being compared as well as the individual observations within the samples must be independent of one another. We need the randomization condition in the sense that subjects are coming from a random sample. We need the equal variance condition, and what we mean here is that the variances of these populations should be approximately equal to one another. We can go back to the previous lecture when we talked about the pooled variance, and we can invoke the rule that the largest sample variance should not be more than twice as large as the smallest sample variance. And we also need the nearly normal condition. The distribution of all of our sample means are all approximately normal. So for our example, we're going to set the null hypothesis as the mean math SAT score for computer science majors is equal to the mean math SAT score for economics majors, which is also equal to the mean math SAT score for history majors. The alternative hypothesis is going to be at least two of these mean math SAT scores are not equal. Now what you're going to see here is that we won't necessarily know which means are not equal. We won't know how many pairs of means are not equal, but the alternative is simply telling us that at least two of these means are not equal. There's some difference somewhere among at least two of these means. So our next step is to go ahead and check the conditions. If we go out and we randomly sample 5 students from each of 3 different majors, the independence condition is certainly going to be satisfied. The groups are going to be independent of one another unless a student happens to be double majoring in 2 of these 3 majors. And while these students are at the same university, the students' math SAT scores are likely independent of one another because they probably came from very different locations whenever they were taking the SAT. The randomization condition is also going to be satisfied. The subjects were randomly sampled from a university, so we very likely have a representative sample of students from this university. Now, taking a look at our samples, in column B, we have our 5 computer science math SAT scores. Column C contains the econ scores, and column D contains the math SAT scores for our history majors. Now, looking over at the box plots on the right, we can see that all 3 of these samples look to be very symmetric, indicating that they're probably close to being normally distributed. Looking at the sample statistics that we have in rows 8, 9, and 10, what we can see is that the sample mean for the computer science majors is 720, sample mean for econ is 640, and the sample mean for the history majors is 536. Looking at the sample variances will allow us to check to see if the equal variances condition is satisfied. Notice that the history sample variance is 6630, the computer science sample variance is 3650. These are the largest and the smallest, and because the history sample variance is less than twice as large as the computer science sample variance, the equal variance condition is going to be satisfied here. So more formally, going back to our conditions, the box plots did show similar spread across all majors, and mathematically, the largest sample variance from the history majors was less than twice as large as the smallest sample variance, which came from the computer science majors. And the nearly normal condition was satisfied as well, because all of our box plots did look very close to being symmetric, so we are pretty safe in saying that the shape of the sample mean is approximately normal for all 3 of our groups. In ANOVA, we need to also calculate out the grand mean. The grand mean is the mean of all of our observations, ignoring the group from which the observation was sampled. The grand mean is denoted by Y double bar, and it's calculated by taking a weighted average of your sample means. So what we can do is we can take the sample size for the first group, N1, multiply that by the sample mean for the first group, Y1 bar, add on the sample size for the second group, N2, times the corresponding sample mean for the second group, and then continue to add on the sample size times the sample mean for each of our remaining groups. We'll then divide that sum by the total number of observations that we have altogether across all of our samples. This value is going to be used in the calculation of the between group variation because this number is going to help us understand how different these sample means are from one another. One thing that I do want to warn you about is that you can't necessarily just average the sample means in order to get the grand mean. Averaging the sample means is only going to work if all of your sample sizes are the same. So in general, because you don't have to have the same sample size in each group, averaging the sample means will generally not work. Recall that the between group variation is looking to measure how different the sample means are. Between group variation is denoted by SSTR for sums of squares due to the treatment, and it's calculated by taking the sample size for each group and multiplying it by the squared difference between each sample mean for the group and the grand mean, y double bar. We repeat this calculation for every single individual group that we have, and that sum is going to give you your between group variation. The within group variation, again, is trying to measure how different the observations are within each individual group. Within group variation is denoted by SSE, and this is calculated by taking the sample size for the group -1, multiplying it by the corresponding sample variance, and again, repeating this calculation for every single group and adding up all of these individual products. So for our example, we first need to calculate out the grand mean. Y double bar is going to be calculated by taking the sample size for the computer science majors, which was 5, and multiplying that by the sample mean of the computer science majors, which was 720. We then add on the sample size for the economics majors, which was again 5. Multiply that by the sample mean math SAT score for the econ majors, which was 640. And then do the same thing for the history majors. Add on 5 times their sample mean of 536, dividing that sum by the overall number of observations that we have in total, which is 15, gives us 632 as our grand mean. This 632 is telling us that the 15 students in the sample averaged 632 on the math part of the SAT, ignoring that student's major. Then we need to calculate out the between group variation. The between group variation, or the SSTR, is calculated by taking the sample size for the group, which is 5 across the board, and then multiplying it by the squared difference between each sample mean and the grand mean. So for the computer science majors, we have 5 times the quantity 720, which was their sample mean, minus the grand mean of 632 squared. Then we do the same thing for the econ majors, 5 times 640 minus 632 squared, and then add on the same factor for the history majors. They averaged 536 on the math part of the SAT. The grand mean was 632. Working out each of these individual components gives us 38,720 as the contribution to the between group variation for the computer science majors, 320 as the contribution from the econ majors, and 46,080 as the contribution from the history majors. Notice that as the group's sample mean gets farther away from the grand mean, the contribution to the between group variation gets larger. This is the reason the econ majors had the smallest contribution of 320, and the history majors had the largest contribution at over 46,000. This sum gives us our between group variation, or SSTR, of 85,120. Now to calculate out the within group variation, or the SSE, we'll take the sample size for the group, -1, and multiply by the corresponding sample variance. So for the computer science majors, we have 5 minus 1 times their sample variance of 3,650, which we calculated a couple of slides ago in Excel. Then we add on 5 minus 1 times 4850 for the econ majors, and then add on our third factor, 5 minus 1 times 6630 for the history majors. Notice again that each group is going to make some kind of a contribution to the total SSE. Groups that have smaller sample variances are going to make smaller contributions, so the computer science majors make the smallest contribution to the SSE, while the history majors make the largest contribution. And this sum gives us our total within group variation of 60,520. Before we can go into how to analyze the results, we first have to talk about a new distribution. The F distribution is a continuous probability distribution that has a number of properties that are different from the normal and t distributions. The F distribution is unimodal and right skewed. So looking over at the graphs that we have on the right hand side, we have 4 different F distributions. Notice that all 4 of them have their peaks somewhere between 0 and 1, and they all extend out to the right towards positive infinity with really long right tails. The F distribution is always non-negative. The smallest value it can possibly take on is 0. There are actually 2 parameters for the degrees of freedom in the F distribution, one for the numerator and one for the denominator. And the F distribution is used to compare the ratio of 2 sources of variability, which is why it's so useful for ANOVA. In ANOVA, we have 2 sources of variability. We have between group variability and we have within group variability. So our test statistic is going to follow an F distribution with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator. It's calculated by taking the ratio of our between group variation and the within group variation. The numerator is the sums of squares due to the treatment, the between group variation, divided by k minus 1. The denominator is the within group variation, SSE, divided by its degrees of freedom, n minus k. This then gives us the mean squares due to the treatment, MSTR, divided by the MSE, the mean squared error, as our test statistic. So going back to our SAT example, the first thing that we need to do is calculate out the degrees of freedom. We have 3 different groups that we're comparing, computer science, economics, and history. So k is equal to 3, giving us 3 minus 1, or 2 degrees of freedom in the numerator. As for the denominator, we have 15 observations altogether, 5 from each of our 3 different groups. We take the 15, subtract off the number of groups that we're comparing, which is 3, to get 12 degrees of freedom in the denominator. To calculate out the mean squared treatment, or the MSTR, we take the between group variation, 85,120, and divide it by its degrees of freedom, 2, to get 42,560 as our MSTR. And to get the mean squared error, the MSE, we take the SSE, our within group variation of 60,520, and divide it by its degrees of freedom of 12 to get our MSE of 5,043. So to finish off the mechanics, what we can do is we can take our mean squared treatment, 42,560, and divide it by the mean squared error, 5,043, to get our test statistic of 8.44. Now, a couple of things about this test statistic. First of all, the test stat in ANOVA does not have a nice interpretation. It's really just a measure of how large your between group variation is in relation to your within group variation. The second thing to keep in mind is that ANOVA is actually always going to be an upper one-sided test. We're always going to be looking at the area in the upper tail of the distribution, because the larger this ratio is, the more variation we have between our group means, and the less variation we have within the individual samples. So the larger this test statistic is, the more evidence we have against the null hypothesis, the more evidence we have supporting the notion that these means are not actually all equal to one another. Now, our test statistic here has 2 and 12 degrees of freedom, which is the F distribution that you see over on the right. However, just like with the t distribution, there's no nice, easy way to find corresponding p-values or probabilities using the F distribution. So we have to resort to using software, and if we use Excel to find this corresponding area up above 8.44, we find that the p-value is 0.003. So considering we have a very small p-value, 0.003, which is less than the common 5% level of significance that's typically used, we are able to reject the null hypothesis, and we're able to conclude that the mean math SAT scores are not all equal for computer science, economics, and history majors. Now, notice that the conclusion that we made here was that all three of these means are not equal to one another. This is one limitation of OneFactor ANOVA. OneFactor ANOVA can only determine if a significant difference exists between these means. It can't determine exactly where that difference actually lies. That's a topic for multiple comparisons, which we're going to tackle a little bit later on in this lecture. Now, all of these sums of squares and degrees of freedom that we just looked at can be summarized nicely in an ANOVA table. In the ANOVA table, the top row contains all of your information about your between group variation. The second row contains all of your information about the within group variation, and then the third row contains your totals. Notice that the second column contains your sums of squares. We have the SSTR, the between group variation, the SSE, the sums of squares due to the error, and the SST. This column is additive. You can take the sums of squares due to the treatment, add on the sums of squares due to the error, and get your total sums of squares. The next column gives us our degrees of freedom. We have k minus 1 degrees of freedom in the numerator, n minus k degrees of freedom in the denominator, and adding those together will give us the total degrees of freedom altogether, which is n minus 1. If we then take the sums of squares and divide by their respective degrees of freedom, we get our mean squared terms. MST is SSTR divided by k minus 1, and MSE is the SSE divided by n minus k. In the final column, we then have our test statistic. The MST divided by the MSE gives us our F statistic, which has k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator. So let's work through an example using the ANOVA table. In this case, we have a large department store, and they're giving out scratch-off coupons at the door that are for 15, 20, 25, or 30% off the entire purchase. We randomly sample 72 customers, and we record the total amount of their purchase before applying the coupon. We want to know if these customers are spending different amounts before the coupon is applied, depending on the percentage off that they received on this coupon. So our null hypothesis here is that our four population means are all simultaneously equal to one another. The average that someone spends who has a 15% off coupon is equal to the average that someone would spend with a 20% off coupon, which is equal to 25%, which is also equal to 30%. The alternative hypothesis here is that at least two of our mean purchase totals are significantly different. Now, rather than going through all of the conditions, let's just assume that they all hold for this situation. Now, given the data in Excel, we have the 15% off prices in column A, 20% off in B, 25% in column C, and 30% in column D. Notice here we also have different sample sizes. We have the most people who got 15% off and the fewest people who got 30% off. Now, in Excel, if you want to run a OneFactor ANOVA, what you can do is click on the Data Analysis Toolpack and select ANOVA Single Factor from that menu. Once you select that option, the box that you see in the bottom right will show up. In Input Range, you should select all of your data as well as the column headings. So here we're going to select cells A1 all the way down to D26. If you have unequal sample sizes, it doesn't matter if you have blank cells included in here. You just need to make sure that you've included all of your data. Because we have the variable names in the top row, we want to check the box that says labels in first row. and then click OK. Now, given the information that we have on this slide, we can actually fill in the entire ANOVA table. We know that the between group variation is 4,627. We know that the total amount of variability is 78,833. So subtracting the between group variation from the total gives us our within group variation of 74,206. In terms of the degrees of freedom, we know that we are comparing 4 different groups. So we're going to have 3 degrees of freedom in the numerator. We have a total of 72 observations altogether. So 72 minus the 4 groups that we're comparing gives us 68 degrees of freedom in the denominator. And then 3 plus 68 gives us 71 degrees of freedom in total. Taking the 4,627 for the between group variation and dividing by its degrees of freedom gives us 1,543 for the mean squared treatment. And then taking the 74,206 and dividing by 68 gives us the MSE of 1,091. The ratio of these two mean squared terms will then give us our test statistic of 1.414. Now, in Excel, if you click OK after selecting your data, you'll get an output that looks like this. Up at the top, you'll get a summary of all of the statistics for each of your individual groups. So we can see that the people who had the 20% off coupon actually spent the least at $140.64, while the people with the 30% off coupon spent the most at $165.3. We can also see that the sample variances allow the equal spread condition to hold because the largest variance is less than twice as large as the smallest variance. Down below, you will then get your ANOVA table. And notice this is the exact same table that we just filled in. We have the same sums of squares, degrees of freedom, and the same F statistic that we calculated out. However, Excel is also going to give you the p-value. In this case, our p-value is 0.2464. And then column G will give you a critical value, assuming a 5% level of significance. So if your test statistic ends up being larger than this critical value, which it's not in this case, then you will have a p-value that is less than 0.05. So in terms of summarizing our mechanics, we have 3 and 68 degrees of freedom. We have a test statistic of 1.414. And we have a p-value of 0.2464. What this means in terms of our conclusion is that we're going to end up failing to reject the null hypothesis. And this will allow us to conclude that the amount of money that people spend at this department store does not differ based on the value of the coupon that they received. There is not a significant difference in any of the 4 group means, 15, 20, 25, or 30% off. So that's telling us that people tend to spend the same amount regardless of the amount of the discount that they are going to receive. Now, whenever we find a significant difference in ANOVA, as we did in the first example with the math SAT scores, the only conclusion that we can make is that at least 2 of these means are not equal. This is a problem because there are several different ways that we could potentially reject the null hypothesis. Consider this first set of situations. We could have a situation where one pair of means is not equal, but the other 2 pairs are not significantly different from one another. We could have a situation where exactly 2 pairs of means are not equal to one another, but the other pair does not exhibit any significant difference. Or we could have a situation where none of our means are equal to one another. All 3 of them are significantly different. This gives us 7 different possible ways that the null hypothesis could be rejected, and that's only with 3 means. This number is only going to grow exponentially as we compare more and more means. As a result, we need some kind of a way to determine which one of these situations is the reason that we rejected the null hypothesis. And the solution to this is to use multiple comparisons. Multiple comparisons is a procedure that we use to determine exactly which pairs of means are significantly different from one another in ANOVA. Multiple comparisons can be thought of as an extension of ANOVA. It's a procedure that you do after completing the hypothesis test. What we do is we calculate a confidence interval for every pair of group means, but we make an adjustment to this confidence interval based on how many comparisons we need to make. Now, there are a lot of different techniques for performing multiple comparisons. We have Fisher's least significant difference method, we have the Bonferroni adjustment method, and we have Tukey's method of multiple comparisons. Now, the one that we're going to focus on is Fisher's least significant difference method. Your textbook mentions the Bonferroni adjustment method in passing, but in my opinion, it does a very poor job on elaborating on this. So I would not rely on the textbook for notes on multiple comparisons. I would focus a little bit more on what I'm going to cover here over the next few minutes. Fisher's least significant difference method of multiple comparisons, or Fisher's LSD method for short, is a method of multiple comparisons where for every possible pairing of group means, we calculate a confidence interval. We take the difference between the two sample means that we're interested in comparing. We add and subtract some critical value from the t-distribution that has n minus k degrees of freedom. This is the same as the denominator degrees of freedom from your ANOVA table. Then we multiply that by the square root of the MSE from the ANOVA table times 1 over Ni plus 1 over Nj, which are the sample sizes of the groups that you are comparing. Now, if this confidence interval does not contain 0, then we're able to conclude that these means are significantly different. One of the two is significantly larger than the other. If the interval does contain 0, then we're not able to identify any significant difference between the two because it's going to contain both positive and negative values, so either mean could plausibly be larger. So let's go back and look at our SAT example. We were comparing the average math SAT scores for students in 3 different majors: computer science, econ, and history. Looking at the ANOVA table, we had an F statistic of 8.44. That gave us a very small p-value, and it gave us strong evidence that at least 2 of these means were significantly different from one another. Now, the 2 values that we're going to need from the ANOVA table in order to calculate out our Fisher's LSD confidence intervals are the degrees of freedom from the denominator, which is 12, and the MSE, which is 5,043. Now, because we're comparing 3 different groups, we want to compare every single possible pair of group means. And in this case, what that means is that we need 3 different confidence intervals. We need to compare the means for the computer science majors against the mean for the econ majors. We need to compare the average math SAT score for the computer science majors and the history majors. And we also need to compare the average math SAT scores for the econ majors against the history majors. Now, as we saw before, this number is going to grow very quickly as the number of groups that we compare increases, and it's always best to use software in order to find these intervals if you have more than 3 that you need to calculate out. Now, our first step in calculating out Fisher's LSD confidence intervals is to find the margin of error. The critical value for 95% confidence interval with 12 degrees of freedom is 2.179. And again, we can find this value just by looking it up in the t-table and intersecting the column for 95% confidence with 12 degrees of freedom. The MSE from the ANOVA table is 5,043, and we have sample sizes of 5 from each one of our 3 groups. What this means is that the margin of error for every confidence interval that we calculate is going to be 2.179, our t-statistic critical value, times the square root of the MSE, 5,043, times 1 over 5 plus 1 over 5. We're only comparing 2 groups at a time, so we only need 2 of those 3 sample sizes underneath the radical. That's going to give us a margin of error of 97.87. Now, I want to point out here that the margins of error for these confidence intervals are all going to be the same because all 3 of our sample sizes were the same. If we have different sample sizes in each group, then we're going to have different margins of error. So each individual confidence interval's margin of error will have to be calculated out separately. So let's go ahead and calculate out Fisher's LSD confidence interval for each pair of group means. Comparing computer science against economics, the computer science majors averaged 720 on the math part of the SAT. The econ majors averaged 640. We're going to add and subtract the margin of error, 97.87. And that's going to give us a lower bound of negative 17.87 and an upper bound of 177.87. Notice that this confidence interval contains 0. What we can also say here is that while the difference in the sample means was 80 points, the computer science majors could average as much as 177.87 points more on the math part of the SAT than the econ majors. But it's also possible that the econ majors scored about 18 points better than the computer science majors. Comparing computer science and history, we do the exact same thing. Take the difference between their sample means, 720 minus 536, add and subtract the margin of error of 97.87. That's going to give us a lower bound of 86.13 and an upper bound of 281.87. Notice that this confidence interval is entirely above 0. So in the worst case scenario, the computer science majors averaged about 86 points better than the history majors. In the best case scenario, the true difference between their means is as high as 282 points. And finally, comparing the econ versus the history majors, we have 640 minus 536, add and subtract our margin of error. That gives us a lower bound of 6.13 and an upper bound of 201.87. This confidence interval is also entirely above 0. So in terms of what we're able to conclude here, we can say that both the computer science majors and the econ majors scored significantly higher than the history majors on the math portion of the SAT, because both of those confidence intervals were entirely positive, and we had the history majors second in the order of subtraction in both of those intervals. However, while we can say that the computer science majors had a larger sample mean than the econ majors, that difference was not statistically significant. The confidence interval between CS and econ contained 0. It had both positive and negative values, so we can't say that either one of the two majors scored significantly better than the other. So to finish things off, let's take a look at the coupon example, and I'll show you how to get these confidence intervals using Excel. Now, reviewing this example, we had 4 different groups, and we were looking to see the average amount that these people tend to spend, given a 15% off coupon, 20%, 25%, or 30% off coupon. Looking at the sample sizes, notice that they are all different. So we're going to have different margins of error for every confidence interval that we calculate. Looking at the ANOVA table, we had an F statistic of 1.414, which gave us little to no evidence of a significant difference. And again, the 2 values we need to pull from this table are the degrees of freedom for the denominator, which is 68, and the mean squared error, which is 1091. Now, thinking about the result of the ANOVA test, we actually already know something about these confidence intervals. Without doing any type of calculation for these multiple comparisons confidence intervals, we immediately know that every single one of these confidence intervals is going to contain 0. Whenever we ran the ANOVA test, that allowed us to conclude that the average amount people spend with a 15% off coupon equals that for 20%, which is equal to 25, which is equal to 30%. So the takeaway here is if you fail to reject the null hypothesis in ANOVA, because the conclusion in ANOVA tells you there's no significant difference, you automatically know that every single one of your multiple comparisons confidence intervals is going to contain 0. So as a result, there's really no need to perform the multiple comparisons analysis because you already know what every single confidence interval is going to tell you. You already know that every single interval, because it contains 0, is going to say that there's no significant difference between the pair of group means that you're comparing. However, I do want to show you at least how to calculate these confidence intervals using Excel. It's incredibly messy. The data analysis toolpack doesn't actually do it, and it may actually be a little bit easier to do these out by hand using a calculator. However, I do want to at least show you these calculations. In row 1, we have the degrees of freedom, which is 68. Row 2 contains our mean squared error of 1091. Rows 5 through 10 contain the information for the different comparisons that we're making. Now, notice that because we have 4 different groups, we actually have 6 different comparisons. We have to compare the 15% off to 20, 25, and 30. We have to compare 20% off to 25 and 30. And then we have to compare 25% off to 30% off. Columns C and D contain the first group mean and the second group mean. Columns E and F then contain the corresponding sample sizes. Now, in order to calculate out the confidence intervals for each pair, I've done that down in rows 13 through 18. What you see in cell C13 is the calculation of the margin of error. That was calculated using the formula that you see down in cell B21. We take the t-statistic to get your critical value, multiply that by the square root of the MSE up in cell B2, which is 1091, and then multiply that by the sum of the reciprocals of the sample sizes. So, for example, we have 1 over cell E5, which is 25, plus 1 over cell F5, which is 21. That will give us the margin of error that you see in cell C13. At that point, what we do is we take the difference between the group means that we're comparing. So in cell D13, we have 149.558 minus 140.638. We're then going to subtract off the margin of error of 19.512. In cell E13, we're going to do the opposite. Right? We will take the difference between the sample means, but we'll then add on the margin of error. That's going to give us our confidence interval of negative 10.592 up to positive 28.433. You can then repeat that process for the remaining 5 confidence intervals to get the intervals that you see in columns D and E and rows 14 through 18. So the last thing that I want to address in this lecture is the relationship that exists between the widths of the intervals. So if we take a look at the groups that are comparing the 15% off coupon to the 20% off coupon, those groups had sample sizes of 25 and 21, giving us a confidence interval width of 39.025. If we look at the one at the very bottom, where we have 25% off compared to 30% off, we had sample sizes of 16 and 10, which gave us a confidence interval width of 53.145. And so if you look at everything in between, we have this relationship between how large the sample size is and how wide the interval is. That relationship is that confidence intervals that are comparing groups that have larger sample sizes end up being narrower.